All right, last video. So number 39 from chapter 11. Let's do this and then we'll do number 43. So it tells me that the angular momentum of a flywheel having a rotational inertia of 0.140 kilogram meters squared about its central axis decreases from 3 to 0.8 with the correct units in 1.5 seconds. So let's write down what all that means in terms of actual parameters here. Okay, my Apple pencil stopped working just a second. All right, that was weird. All right, so the first thing it says, it's being crazy over here. Hopefully this will still work. Just one more second. Okay, goodness. So it says having rotational inertia of 0.140 kilogram meters second. So a rotational inertia, remember that's I. And it also has the units for I, kilogram meter squared. So that's our rotational inertia, or moment of inertia, about the central axis. And it's moving around, so it says the angular momentum about its central axis decreases from 3 to 0.8, and then it's got these units, kilogram meter squared per second. So this is angular momentum initial is the 3 kilogram meter squared per second, and the angular momentum final is 0.8 kilogram meter squared per second. And again, you have to put the units in the whole time. And the time it takes to do this is 1.5 seconds. So it says, what is the magnitude of the average torque acting on the flywheel about the central axis during this time period? So the average, remember that the net torque is going to be the derivative of the angular momentum with respect to time. Well, here I actually have a final and an initial, so the average net torque is just going to be the change in angular momentum over time. So it's going to be L final minus L initial over the time it took here. So for us, that's 0.8 minus 3. 0.8 minus 3 divided by the 1.5 seconds. So I end up with an average torque of negative 1.47, and this is a Newton meter because it's a torque. So that's my average torque. It actually says the magnitude, so technically that would just be 1.47, but I'm going to leave it with what we've got there. But if you looked at the text, it would probably say positive 1.47 because it's saying the magnitude. So the magnitude would just be 1.47 Newton meters. It says assuming constant angular acceleration, so assuming that we didn't have some changing thing here, through what angle does the flywheel turn? All right, so for part B, so this was part A. For part B, it wants to know through what angle does the flywheel turn, or this is theta final minus theta initial. Well, to do that, I need to I know tau, I know the net torque, but I don't know alpha. I do know time. So I probably need to figure out some other variables. But if I know net torque, that means I can figure out alpha. And I also know I. So alpha, the angular acceleration, is going to be my net torque divided by I. And I am going to use the 1.47 here, the negative, divided by 0.140 kilogram meter squared. So when I do that, oh goodness, divided by 0.140, I get a negative 10.5, and this is going to be alpha, so my units come out to be radians per second squared. I can actually prove that. So a Newton meter divided by a kilogram meter squared. A Newton is a kilogram. This top is actually a kilogram meter squared per second squared divided by a kilogram meter squared. And so the kilogram meter squareds go away, and all I end up with at the top is actually a blank, but there's actually a radians there. There's a radians there. So when I cancel out everything, there's still a radians on the top. It's not degrees, it's radians. So that's my alpha. I also know time, right? I still know that time is 1.5 seconds. In order to find out delta theta, I probably need some initial omega or some final omega. So I should also say that L initial is I omega naught. And so I can get the omega naught by taking the initial angular momentum and dividing it by the moment of inertia. So my initial was 3 kilogram meter squared per second, and my I is 0.140 kilogram meter squared. And so 3 divided by 0.140 is 21.4. And again, my kilogram meter squareds go away, and I end up with a per second, but this is omega, so my units are really 21.4 radians per second. All right, so now I have omega naught and alpha, and I can use that delta theta is omega naught times time plus 1/2 alpha t squared, right? This is very similar. This is the equivalent to this equation from linear motion. Plugging all those in, just a second, and I'll get those calculations. So when I go and do that, I get 20.3 radians, and that's radians. That's all the units that are left. I could have, by the way, I could have used another equation. I could have used, if I had taken LF and known that that was I omega F, I could have solved for omega F, and then I could have used some of the other equations as well to get delta theta. Either way, I'm going to get 20.3, so you should get that number no matter how you go about doing it. So that's part B. How much work is done on the flywheel? Let's add another piece of paper here. So part C, what's the net work being done? Well, the net work, I can just do that. It's probably, the net work, if we go back and we look at our equations over here, it's going to be, I don't know if we want to do it through kinetic energy. So net work can be either, we can say final minus initial kinetic energy, or we could do it through the torque, the net torque, and our delta theta. Right, net work, sorry, this is so far back, but the work done, where is our, there it is. So the work done by a torque is the torque times the delta theta, but if you know the net torque, then the net torque would stand in here and the delta theta would go in there, and this would become the torque done by the net torque. So I don't know which one of those would be simpler. I'm going to probably do this one because I know the net torque and I know delta theta. So my net torque was blah, 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 negative 1.47 Newton meters. And the delta theta, which we just did, was 20.3, a positive 20.3 radians. And I end up with a negative, let's double check this. So times negative 1.47 is negative 29.9 joules. I'm taking away that energy from it. Does that make sense? Is it moving slower afterwards? It is moving slower afterwards, right? It has a slower final angular speed than an initial angular speed. Initially, it's moving at 21.4. If I actually went through and did the final, if I did L final divided by I, L final is 0.8 divided by 0.14. It's only moving at 5.71 radians per second. So it's spinning faster initially than finally, which means it's losing kinetic energy. And if it's losing kinetic energy, that means that something is taking the energy out. And that means the work is negative, much like friction does that. All right, so then the last question is, what is the average power on the flywheel? So average power is work over delta T, just like we had before. So this is work. So we've got the 29.3 joules over the time it took for this to happen, which is 1.5 seconds. And that comes out to be 19.9 joules per second, or negative 19.9 joules per second. So that's the energy that's coming out of the flywheel, I guess, is really what we're talking about. So I think we're going to go, I've got that we're putting in a positive here. I guess this is the work done to the wheel. But the flywheel itself, I guess that's true. The work of the flywheel. So the flywheel is sort of is the opposite. It's the positive 29.9 joules. And so this would be a positive and a positive. I think the flywheel is putting that work into something else, right? It's the flywheel's losing energy, but that means that it's putting energy into something else. So this is the output work of the flywheel is a positive 29.9 joules. Sorry, guys. Yeah, 29.9. All right. Let's look at the last problem I want to do, which has to do with the fact that we have conservation of angular momentum. So going back, I just sort of did this briefly in that last video, but if the net torque on a system is 0, then the angular momentum initially of that system is equal to the final angular momentum, or angular momentum is conserved. Again, this is very similar to when we had collisions and we said if the net force was 0, the external force on something on the system was 0, then the P initial was equal to P final. But now we have angular momentums and torque. So we have two skaters, and they're approaching each other, and they both have the same mass. They have 50 kilograms mass. They approach each other along parallel paths, separating by 3 meters. They have opposite velocities of 1.4 meters per second each. So let me just do a little, well, I've got the sketch here. So they're both coming in here with 1.4 meters per second velocity. And then they're going to grab a hold of this pole. And as they do that, that's going to cause them to start spinning around, right? They're going to start moving around their common center of mass, which will be right in the middle because they have the same amount of mass. So that R that they're going to be spinning around here, right? If the total thing here is 3 meters, then the R that they're going to be from that axis is going to be the 1.5 meters. So the very first question they ask us, so those skaters then rotate around the center of the pole, assume that the friction is negligible. So that means this is what we're saying. So when we say the friction is negligible, that's how we know the net torque is 0. There's not going to be any forces. What's the radius of the circle? Well, that's what we just did. The radius of the circle that they're going to go on is going to be 1.5 meters. What's the angular speed of the skaters? So the angular speed of the skaters is what we want to know here. Well, I know that they were moving at 1.4 meters per second. Their tangential speed is 1.4 meters per second, and the tangential speed is supposed to be r times omega. So that means omega is 1.4 meters per second divided by 1.5 meters, which gives me an angular speed of 0.933 radians per second. So that's part B. My angular speed, this is a nice, just has like all of our words. I'm trying to make sure we get our vocabulary here. And then it says, C, what's the kinetic energy of the two skater system? Well, the kinetic energy is 1/2 I omega squared. Well, I know omega, but I need to know what I is. If I have two objects, the I for these two objects around their center is going to be, if I only had one of them, it would be the mass of one of them times how far away is that from the place where it's moving squared. But if I have two of them, I just add that together. So for the first one, I have 50 kilograms, and it is 1.5 meters away from the location around the axis. And then I have the same thing for the second one because they're the same mass and the same distance from the location that they're spinning around. So if I go through and do that, just a second, I get 225 kilogram meters squared. So then if I plug that in here to 1/2, 225 times 0.933 squared, I'm going to get a K of, again, let me pause. I get a K of 97.9 joules, right? It's kinetic energy. It should come out to in units of energy. All right, now it says, now the skaters pull along the pole until they are separated by only 1 meter. Whoa, so they're being tricky here. So they're going to pull along. So then now their new R is only half a meter away. Their old R was 1.5 meters, but now they're only this. Just 1 second. And it wants to know what's the new kinetic energy, right? So the kinetic energy is not conserved here. So this was we're going to call this sort of our initial. We want to know this. K initial is not equal to K final. There's not that kinetic energy is conserved. What's conserved here is angular momentum, right? Angular momentum is conserved. So what I need to know, I know my initial angular momentum. That's what I found. Actually, I don't know my initial. So let's figure out our initial angular momentum. Our initial angular momentum should be our initial moment of inertia times our initial angular speed. And so all of these are actually initial values that I've got up here. So my initial angular momentum moment of inertia was 225 kilogram meters squared times 0.933 radians per second. And so that's 225 times 0.933. That's 209.9 kilogram meters squared per second. That's my initial angular momentum. That has to equal my final angular momentum, which is I final omega final. That also has to equal 209.9 kilogram meters squared per second. I final, so I need to recalculate this, is going to be M1 R1 squared, M2 R2 squared, where these are the final R's. So now I'm not 1.5, they're not 1.5 kilometers away, they're only half a meter away. And so my new moment of inertia is only 25 kilogram meters squared. The old moment of inertia, remember, this was the 225. So their inertia has gone down tremendously. Remember, moment of inertia is how we quantify inertia. When they're closer together, they have a lot less inertia. They're further away from, when they're closer to that axis, so it's a lot easier to change their rotation speed. So we can use this I final along with the values up here to get omega final. So 209.9 divided by 25. In our omega final is going to be 8.4 radians per second. What is it actually? It wants to know in part D their angular speed. So what's the angular speed? Sorry, so D wants to know the angular speed. I jumped ahead there. So I used the conservation of angular momentum to find that. Basically, I say, well, the initial angular momentum has to equal the final angular momentum. I already knew this, and I actually had to go find my final moment of inertia to be able to solve for the final angular speed. Then in part D, now it wants to know K final. Well, that's 1/2 I final omega final squared plugging those in. Is a whopping 882 joules. Remember that our initial kinetic energy was only 97.9 joules. So we have a huge increase in this. So there had to be some work that occurred here. So this is an increase in kinetic energy this is rotational kinetic energy that we've had. And so we've actually produced, let's see how much that is, 784 joules, roughly, of kinetic energy. And that's going to have come from some torque, some net torque, sometimes some delta theta, which doesn't actually ask us to figure out what that is, but it does say, where is that energy? Where did it come from? What did the work? Well, when they did this, they had to pull along the pole. They had to pull on the pole. They both had to do it. And so the work came from the skaters themselves. Oh, goodness gracious. Pulling force, which allowed them to speed up, to move in at a smaller radius, but they actually did this. So that would have actually been difficult for them to pull in, and that increased that pulling force produced a net torque, which produced the change in the kinetic energy. All right, if you have any questions about any of these, we can bring them up in lecture this week as well, certainly on Tuesday, but definitely look them over.